Good morning everyone. I am Dr. Krishna Dinda. Today I will discuss one of the most fundamental and widely used results in probability and statistics, the central limit theorem, or in short form CLT. This theorem plays a central role in statistical inference and explains why the normal distribution appears so frequently in real-world data analysis. To understand CLT properly, I will first explain why we need it, then briefly discuss its theoretical idea, and finally show how it works in practice. In practice, most real-world data such as income, rainfall, exam score, or mineral grades are not normally distributed. They are often skewed or irregular. However, many commonly used statistical methods such as t-test, ANOVA, and regression analysis assume that the data are normally distributed. This naturally raises an important question. If real data are not normal, why do these methods still work so well in practice? The answer lies in the central limit theorem. The central limit theorem tells us that even if the original population distribution is not normal, the sampling distribution of the sample mean becomes approximately normal when sample size is sufficiently large. This result is extremely powerful because it allows us to construct confidence interval, perform hypothesis testing, and use Z and T distribution in practice. In short, the central limit theorem forms the theoretical foundation of statistical inference. The importance of this theorem lies in the fact that it bridges the gap between theory and practice. Even when the underlying data are not normal, CLT allows us to apply normal-based inferential methods reliably. This is why CLT is indispensable in data analysis, uncertainty quantification, and decision making under randomness. But to appreciate its value fully, let us briefly see what existed before CLT. Before the CLT, mathematicians were already familiar with results such as the law of large numbers and services inequality. These results tell us that the sample mean converges to population mean, however, they do not describe the shape of the sampling distribution. They tell us where the mean goes, but not how it is distributed. The idea that the sampling distribution becomes normal was first observed by Laplace, later rigorously developed by Lyapunov, and the term central limit theorem was popularized by the mathematician George Polya. Now students are ready for mathematics. Formally, for this theorem, we consider a sequence of independent and identically distributed random variables with finite mean and variance. When we standardize the sample mean, we subtract this population mean and divide by the standard error. The resulting variable converges in distribution to a standard normal distribution as the sample size tends to infinity. Here I will not go into the full technical proof, but the key idea uses moment generative functions. Since moment generative functions uniquely determine the probability distribution, showing that moment generative function of standardized sum converges to a moment generative function of a normal distribution implies convergence in the distribution. This provides a rigorous mathematical justification for the theorem. To build intuition, consider a simple real-world example. Suppose we roll a fair die. We observe that the outcome of a single roll is not normally distributed. However, we roll the die many times and compute average outcome repeatedly. We observe that the distribution of this average becomes bell-shaped. As the number of trials increases, the distribution of sample mean approaches a normal distribution. This phenomenon is a direct illustration of the central limit theorem. Although central limit theorem is powerful, it has some limitation. The assumptions for these theorems are observation must be independent and identically distributed, and the population variance must be finite. For small sample sizes or habitual distribution, the normal approximation may be poor. Therefore, it is important to verify assumption before applying CLT in practice. Therefore, we conclude that the central limit theorem states that as the sample size increases, the sampling distribution of the sample mean approaches a normal distribution, regardless of the underlying population distribution. This result forms the backbone of inferential statistics and justifies many commonly used statistical procedures across a wide range of scientific and engineering applications.